The next function that we want to look at graphing and determining some different characteristics from is a logarithmic function. Okay, a logarithmic function, which we can also look at something called a natural log function, is going to be an inverse function of our exponential. Okay, remember, if we think back, an inverse is just the opposite, right? So remember, we were switching the x and y, we're doing all of those things. It was an inverse function. So since we know that a logarithmic function is an inverse of our exponential function, if I know how to graph an exponential, then I can basically graph a logarithmic function, because all I will need to do is switch everything. So think about what we know about an exponential. Remember, on an exponential function, we had a horizontal asymptote, which means this time we're going to have a vertical asymptote. In an exponential function, our domain was all real numbers. So in a logarithmic function, my range will be all real numbers. In an exponential function, our range included the horizontal asymptote to infinity. This time, our domain will include the vertical asymptote to infinity. In an exponential function, we had the points 0, 1, 1 the base. This time in a logarithmic function, we have the points 1, 0, the base 1. So honestly, all we're doing when we graph a logarithmic function or come up with the different elements is doing exactly opposite of what we did before, all right? So that's one way to kind of think about what a logarithmic function is. Right, so first let's look at a graph of what this might look like so we can get an idea of it. So our most basic logarithmic function would look something similar to this. Remember, we said that we are going to have a vertical asymptote. So they did not draw it on here, but a vertical asymptote would be here at x equals 0. Remember, last time we had a horizontal asymptote at y equals 0, so it's going to be opposite this time. All right, we also have the point 1, 0. Okay, then we're going to have the point, the base, comma 1. So I can see here I'm going to have 10, comma 1. Therefore, 10 must be the base of this function. All right, so I can see all of those elements again. And honestly, if I were to turn this graph on its side, I would see an exponential function. So let's look at this for just a second. I'm going to turn it around here. So if I were to take this graph and just literally turn it on its side, I will see that that's an exponential function. Now it has that horizontal asymptote, and it's now going to be exponential, all right? So let me turn this back on its side here. Okay, so we can go back and see that this indeed was our log function, right? So we now kind of see what a log function looks like. So let's look at what the different elements would be if we had an equation, all right? So in our equation here, we notice we've got the same things that we had before in an exponential. We had our h, which is going to move right and left. We had our k, which is going to move up and down. We have this b, which is the base of our function, right? So the little number after the word log is going to be representing our base. Remember, we need our base when we come down here for our for our table. Okay, so again, I can move this function up, down, right, left. I can stretch and shrink it. That means we would have a number in front of our log. I can stretch, shrink, reflect it. And again, that's going to affect some of the different things. So thinking back to an exponential function, remember when we had an exponential function, that movement up and down, that k movement was what was the most important. It determined our horizontal asymptote, and it also determined our range. But this time, instead of looking at the k, we're going to look at the h. So the h value is going to determine our vertical asymptote in our domain. Okay. Now remember, something to think about is that our h is always opposite of what you think. Remember, when we have something that's like x plus 5, a plus 5 really moves to the left. So I have to remember that. That's why sometimes it's a little bit more tricky. All right, so I can come up with the vertical asymptote in the domain by looking at the h value. How do I move left and right? The range this time will always be negative infinity to infinity. All right, so let's look at an example and see if we can come up with not only the elements, but we can also graph it. So let's say, for example, our first equation is f of x equals log base 3 x minus 2 plus a 1. Right, so we want to be able to come up with the different elements about this function. So the first thing that we want to do is we want to say, okay, well, what's the most important here? It's how do we move left and right? So we come up with our domain by coming up with the vertical asymptote. All right, so last time when we did the domain, we didn't have to come up with an asymptote. This time when we talk about a log, we do, okay? So the log is determined, the log's domain and vertical asymptote are determined by our motion left and right. So this function is going to be moving to the right 2, which means that my vertical asymptote is now going to be x equals 2. So my domain will be from 2 to infinity. All right. My range this time is the one that's all real numbers. So there's nothing to really think about on that one. So let's come up with our ordered pairs. All right, let's look at a table. So we start off our table 1, 0, the base, which is that 3, comma 1. But we want to transform this function. So let's see, how are we going to transform it? Well, we already know that it's going to move to the right 2, but we also know that it's going to move up 1. So if I'm moving to the right 2, that means I'm going to be adding 2 to my x's. So I should get 3, 5. And if I'm going up 1, I should be adding 1 to my y's. So I should get 1, 2. So let's go graph those ordered pairs now. Graph those points. So I'm at 3, 1, and I'm at 5, 2. Then we're going to graph now a vertical asymptote at 2. And it's kind of the same idea that we had last time. I'm going to connect the dots. The one that is closer to the asymptote is going to approach the asymptote off to an infinity, whether it be positive or negative. In this case, we're going to go off to negative infinity. So I kind of see that graph appearing there. My points, I kind of made my points go away there, but we can see them still. All right, let's look at another example to make sure that we really understand what's happening here. So let's look at a second function here. Let's say that we have f of x equals log x plus 3 minus 4. All right, so we're going to start off the same way that we did last time. We're going to come up with our domain, which means that we need to know about the vertical asymptote. So this is going to be moving to the left 3 this time, which means I'm going to be x equals negative 3. And my domain would be from negative 3 to infinity. My range is always going to be that all real numbers, or negative infinity to infinity. So let's come up with our table now. So our table is 1, 0. The base, which, wait a second, there's no number there. So one thing that we have to know about in a log function is that a log, see where it says where b or 10 is the base. E is when I have a natural log. So if they change the letters to ln, that means I have a base of e. Now the way that I remember that the base is going to be a 10 if there's no number, well, one, if there's a number, it's quite easy to see what the number is. But if I'm missing a number, I look back at the word log and it's telling me it looks like a 10 right there. So that's reminding me that, hey, the number is a 10 sitting here if they don't write anything there. It's kind of like when we write a square root. We don't write a little baby 2 out there because we just know it's called a square root, so it must be a 2. Same way in a log, if they don't write a base, we just have to know that there's a 10 there. So my base is going to be 10 here, and then it's going to be comma 1. All right, so now we're going to transform this function. We already know that we're moving to the left 3, but we're also going to be moving down 4. So if I'm moving to the left 3, I'm going to subtract 3 from all my x's. So I'm going to have negative 2, and then we're going to have 7. All right, if I move down 4, I'm going to subtract 4 from my y, so I'm going to have negative 4, negative 3. So let's go graph these ordered pairs here. So I'm going to have negative 2, negative 4. And then I'm going to have 7, negative 3. I'm going to make my vertical asymptote at negative 3. And then I'm going to connect the dots, those 2 points, and the closer one will approach that vertical asymptote. So now hopefully we can come up with the different elements, because remember we said, you know, we might not want to go all the way to a graph of a log. I might just want to look at the function and say, okay, well, what is the vertical asymptote? I might want to look at the function and just find the domain, or just find the range, or maybe just find what is the transformation, right? Sometimes I do want to go all the way through and find the graph. So hopefully now from these equations we can come up with all of the elements as well as the graph. Also from a graph we could come up with what are some of the elements. Where's that vertical asymptote? What is my domain? What is my range? Those types of things.